Lecture 13, Part B, on energy density and pressure. You're looking here at a figure where you see a liquid in a ball. Without gravity, the attractions of the liquid molecules, such as surface tension, pulls it together in a perfect sphere. For a gas, another type of fluid, the particles will be simply buzzing around, containing the volume the same size as the container. There won't be any concentration of gas in one location or another that'll be sustained for a long period of time. This is without any gravity. With gravity, of course, the gas will be more concentrated lower down. Gravity pulls down the particles. And the liquid won't stay as a ball suspended in the middle or anywhere else. The liquid will all fall down. But the liquid, all the liquid can't be at the lowest spot. The liquid has to pile up on top of itself. With the liquid up top, in the higher parts, is pressing down the liquid below as it's all being pulled down by gravity. The point of this is pressure is created by gravity. For the liquid, it's the liquid up atop the liquid below that's pressing down on it. So pressure increases in a liquid with depth. Pressure also increases in a gas with depth. There's more gas particles concentrated lower down in a gas than above, but the difference is slight. It's a very minor difference. So in essence, a gas of unless the gas does not change pressure with depth, unless the gas is of very great size or very great volume, very great depth. But for a liquid, since it's so much more dense, pressure increases with depth within a liquid. Because the liquid is trying its best to get as low as possible, the layers of liquid press down the layers of liquid below, but they also will press on the sides of a container, trying in a sense to press the container out so the liquid can flow or fall or seep to fall to lower levels, such as puncturing holes in a container full of liquid. The liquid will squirt out of the holes. It's pressing on the sides of the container. Pressure, therefore, can be related to the forces of a liquid on the sides, the sides or the area of the walls of the container. So another relationship for pressure is force per area. The more force on an area, the more pressure there is, such as the greater the force on the area of the side of the container, the more pressure there will be. So pressure is both an energy per volume, or an energy density, and a force per area. Look at the units and work out how pressure can both be energy density, joules per meter cubed, and force per area, newtons per meter squared. Now we know that if we puncture 3 holes in the sides of a container, the hole at the greater depth in the liquid will have greater pressure and the water will be pressed out with greater pressure to squirt out faster and therefore farther. And that's what you're seeing in the second illustration. The water is shooting out roughly in parabolic paths, but it's shooting out faster where the pressure is greater with greater depth. So the pressure, again, also depends on depth for all types of fluids, for gases, but it's only apparent at much greater depths. Now the global average sea level pressure is 101,300 pascals. As we've already used, this is 101 kilopascals, or roughly 10 to the 5th pascals, is 1 atmosphere. So consequently, we define the standard atmospheric pressure to be 101,300 pascals. Now, in a fluid, pressure depends only on the depth. But this has to be when the water is stagnant, when it's not flowing. If 2 locations are at the same depth, they therefore have the same pressure. If the 2 locations at the same depth have different pressure, then the fluid would flow from one location to the other location of lower pressure from high to low pressure until the two locations at the same depth have the same pressure. Another way of saying it is fluid flows along levels where there's a pressure difference. It stops flowing when the pressures are equal at the same level, the same depth. So the two fish here in the two different containers, since they're at the same level, they're subjected to the same pressure. In fact, anything that's at the same level as the fishes in these drawings are at the same pressure. The sizes of the containers, the shapes of the containers don't come into play. Simply the depth that the fish is beneath the water above determines the pressure. It's the column of water above that's pressing down on the creature that's creating the pressure. So is this possible? Could you ever have a situation where you have a container open to the atmosphere on two different containers open to the atmosphere, but the level of the water rises differently in the different containers? Well, if we simply draw a line from the lower surface in the container on the left to the container on the right where the surface is raised, the lower surface will cross in a depth of the column of liquid on the right. So this would be impossible because the surface pressure for both containers, the pressure at the surface of the liquid for both is 1 atmosphere. But I can't have 1 atmosphere at a greater height than at another location, meaning if I have to go down on the container on the right, go down into the fluid to be at the same depth as the surface of the container on the left, I must have increased my pressure from 1 atmosphere. But then I can't have the surface on the left be at 1 atmosphere. So surfaces have to be at the same level, or fluid always rises to the same level, rising to the same level, so it ends up being the same pressure. So we see in this illustration. P1 has to equal P2 because it's at the same depth and the surfaces are at the same level and every location at the same depth has the same pressure. If P1 were greater than P2, then the water would flow from P1 to P2 until P1 is equal to P2. We can use this knowledge, we can apply this for mechanics. Hydraulics is using fluid pressure to lift heavy objects. So what you're seeing in this figure is a weight, a person of mass 70 kilograms, and therefore a weight of about 700 newtons, is pressing down on a platform. We'll say it's a square platform, which rests upon oil. At the same level is an elephant standing on top of a much larger platform. We'll say he's standing on a rectangular platform of a 2 by 2 meter platform. So the elephant is a weight of 1,200 times G, so roughly 12,000 Newton weight pressing down on a larger platform. But since the platforms are at the same level atop the oil, they must be at the same pressure. So in essence, what's happening is the weight of the human is applying a pressure that must be the same as the pressure created by the weight of the elephant. But how can these two very different weights create the same pressure? Well, we call that pressure as a force per area. So the pressure of the man and the pressure of the elephant must be the same, since they're at the same level atop the oil. But since pressure is force per area, then we have here as a ratio of force per area that is equal for the man and the elephant. So the force is the weight of the man divided by the area, let's say area 1 that the man is standing on, and the weight of the elephant divided by the area 2, the second platform that the elephant is standing on. So the ratio of the weights is opposite the ratio of the areas. Plugging in the mass times G, but G cancels, so it's simply the ratio of the masses to the ratio of the areas, we can figure out the area of the platform that the man is standing on, if we assume that the elephant is standing on a 2 by 2 platform. The weights in the area, the second area that the elephant is standing on is known. Therefore, we can figure out calculate the area of the platform that the man would have to stand on to create an equilibrium situation, to create an equal pressure that the elephant has. The point of this is an ordinary force, the weight of a person, can lift up an extraordinary weight, an extraordinary force lifting up an elephant. So we can translate ordinary forces, small forces over small areas, can be translated into very large forces over proportionally larger areas. That's the idea of hydraulics. Using ordinary forces to lift or to push up to create very large forces over larger areas by having equal pressures. So we know that pressure increases with depth. So similar to what we did with buoyancy in the previous lecture in Part A, an object will have different pressures on it. The bottom of the object will have a greater pressure than the top of the object. What you're seeing here is an equation, P and P naught, the pressure, and P naught, usually the pressure at top or the pressure at the open to the environment, the atmospheric pressure. The difference between P and P naught is due to the difference of the object over its depth. Rho GD is another way of saying the gravitational energy density of the object changes with pressure. The pressure lifts up the object. Something that's being lifted up increases gravitational energy density. This volume that's being lifted up, therefore, increases gravitational energy, and the volume is being lifted up or buoyed up from the buoyancy pressure. Difference in pressure, the loss in pressure from high pressure at the bottom to low pressure at the top, that decrease in pressure from high at the bottom to low at top, that loss in pressure energy density is an increase in the gravitational energy of the volume, rho GD. Again, if we have differences in pressure, we can lift up objects, as we just saw. Or if we have differences in pressure at the same level, fluid will flow along that level. Here we see a wide part of a pipe and a narrow part of a pipe is what I'm trying to illustrate. The water is flowing in the direction V1, flowing from left to right, flowing through a narrow tube and then passing into a wider tube. Does water flow faster in the narrower part or the wider part? Well, as you may know from experience, and you'll see from experiments, water flows faster when it's in a narrow tube, filling the narrow tube, and the same amount of water will slow down when filling the wider part. So water flows faster in the narrow part and slows in a filled tube when it's wider. We can think about this in terms of particles or streamlines. You can go to the animation on this, linked on this lecture slide, and play with the sizes of pipes, the sizes of cross-sectional areas, to see how the flow, the speed of the fluid will change, slowing down when the tube is wide, going faster when the tube is narrow. An analogy we can think about is you want to have cars on a highway, but the cars aren't allowed to have traffic jams. So if the highway starts to narrow, lanes start to disappear. To prevent a traffic jam, the cars have to speed up when they enter the part of the highway where it's the narrow part of the highway. To prevent traffic jams, if we go from a 6-lane highway to a 3-lane highway, the cars have to speed up much faster on the 3-lane highway, as during the merger from 6 to 3 lanes. The cars have to speed up in the narrower part of the highway to prevent the traffic jam. But then the cars can go from the 3-lane to a 6-lane part of a highway and afford to slow down without having to create a traffic jam. There are two ways to describe the flow, or the flow rate, of a fluid. The symbol for flow rate is either Q or I. The text will use Q. I will use I because I is what you'll use for the flow rate of electricity, of charges, of electrons of a current electricity. So I'll be consistent with my flow rates or currents throughout the entire sequence when we get to through electricity. So I'll use I, but keep in mind the same thing as Q, the flow rate, or simply the current. Now what you're seeing in this illustration is I1 splits. The water or the fluid splits to become I2 and I3. So we know that I2 plus I3 must be equal to I1. What flows in to the junction must have split apart. The parts must equal the whole. So sigma I in is equal to sigma I out, meaning we add up the currents in, they must equal to the currents out. What flows in must flow out. This is known as Kirchhoff's junction law. It's not the most brilliant of physical principles. It's simply a conservation of matter. So here's a complicated situation where we have a current going from a narrow pipe to a wide pipe, splitting to two different narrow pipes, joining again at a much wider pipe, then going to another narrow pipe. By using Kirchhoff's law, we know the total current is equal to I in is equal to I out is equal to I1 plus I2. So the current in the narrow pipe must be the same as the current in the wide pipe. What flows in must flow out. The same flow of stuff. So current is a flow rate. Current would be stuff per time, volume per time in this case, volume of a fluid, perhaps volume of water per time. It is not the same thing as speed. It's stuff per time, not distance per time, which is what a speed is. Current is a stuff per time, a volume in this case, of fluid per time. So the current that flows in the narrow pipe, the water will slow down, the volume of liquid will slow down in the wide pipe, but the current will still be the same. It will still be the same amount of stuff traveling at the same rate through the pipes. It'll just widen out. It'll widen out and cover less distance as it widens out, but it'll still be the same flow rate. Another way to think about it is, we can say have 2 liters in the narrow pipe coming in, and the 2 liters will then change their shape to, rather than 2 liters being narrow in the wide pipe, the 2 liters can widen up in the wider part of the pipe, travel slower, but it'll still be 2 liters passing by, let's say, every second. And then the 2 liters would split in I1 and I2, travel at different speeds as they move through, but it'll still be 2 liters per second in our made-up current flowing through these different pipes. So the volume flows at different speeds through the different pipes, but it's still the same amount of volume per time flowing through. Think about it like a chain, where each link on the chain is a certain volume of fluid. The volume of fluid has to move along to keep the same current through all the different pipes. It's like, say, a connection of change or a connection of sushi boats all chained together. They all flow together. If one of them if a current in one location is moving at a greater rate, it's a greater current in another location, then you can get traffic jams where the current and the volume from behind will smush up or push the volume in front and separate from the volume from the back. But that's not allowed. It flows as one big chain. The whole current stays the same through one pipe, even if the pipe changes sizes. So speed and current are not the same. A measurement of the volume can be used to determine the speed the fluid flows. So beware that speed is not the same thing as current. I1 is equal to I2, but the velocity of 1 is not equal to the velocity of 2. So another relationship for current, besides stuff per time, is cross-sectional area times velocity, A times V. So I1 is A1 V1, and I2 is A2 V2. So the current in I1, if the pipe is a width of A1, cross-sectional size of A1, an area of A1, then it has a velocity of V1. Now we know that V2 in cross-sectional area in the wider part, A2, must be slower. So A2 is bigger, which makes V2 slower. If A2 is twice as wide, if the cross-sectional area is twice as great, if A2 is twice as great as A1, then V2 is half of V1. So that A2 times V2 ends up being the same product as A1 times V1. This is only true if the fluid completely fills the tube. So again, I1 in the lower example here is equal to I2 plus I3 plus I4, which means A1 times V1, which is I1, is equal to the products of A times V for 2, 3, and 4. So I is stuff per time or flow rate. The units in this case, the stuff, the volume, is meters cubed per second. So does the water flow faster in the narrow part or the wider part? Well, you know that the water flows faster in the narrow part. V1 is greater than V2 in proportion of how much smaller A1 is than A2. But if it's changing its speed, it must be changing its kinetic energy. So going from tube 1 to tube 2, we can examine the energy differences. There's a difference in kinetic energy. Since V1 is greater than V2, the kinetic energy in 1 is greater than 2. So there's a kinetic energy loss from tube 1 to tube 2. Kinetic energy decrease, kinetic energy density 1/2 rho v squared. There's no difference in gravitational energy, rho gh, from 1 to 2. Guess the heights are essentially the same, or negligible. So therefore, if there's a difference in kinetic energy density, there's got to be a difference in another form of energy to account for the loss, the loss of kinetic energy from the loss in speed from V1 to V2. Since it slows down to V2, it's slowing down, it's losing kinetic energy. So where does the kinetic energy go? It doesn't go into gravitational energy. It's not lifting up any higher or lower. The water is simply slowing down without changing height or pressing on any springs or making any chemical or nuclear changes. So what happens to the kinetic energy? It goes into pressure. So pressure is a form of energy density. It's another energy form. So pressure is an energy density. So if the kinetic energy density decreases, the pressure must increase. So which is a greater pressure, P1 or P2? Since tube 1 has the greater kinetic energy than tube 2, then since there's a loss of kinetic energy from 1 to 2, then the pressure must have increased from 1 to 2. So P1 is at less pressure because the water is going faster, and P2 is at greater pressure because the water slowed down. It's simply a transfer of energy densities. This would be similar to, say, an aneurysm in blood flow, where the pressure starts increasing, the tube, where the blood is flowing through, is getting wider. It's like a traffic jam. Okay, illustrations of the same idea. What you're seeing here is the streamlines, the dotted lines, the streamlines, the flow of the liquid going from left to right in the top picture. Where it's wider, it's at a lower speed. Where it's narrowing down, the fluid can't get any more dense. It can't create a traffic jam. So the fluid must flow faster in the narrower part, going from low speed to high speed. So it increases kinetic energy. So another form of energy has to decrease, and that would be the pressure. So in the wide part, the pressure is great. In the narrow part, the pressure is less, going from V1 to V2 in the bottom illustration. What you're seeing there to record the pressure, or what's called pressure gauges. The pressure gauge records a difference in pressure from inside the tube to outside the tube. It's gauging a difference in pressure. So when the dial is at the top, such as the dial is at the noon position, the 12 o'clock position, or close to it, the pressure is lower, such as P2, the dial is reading closer towards the 12 o'clock position, and P1, the dial is reading closer towards the 6 o'clock position. So P1 on the dial is greater than P2. 0 is at the top, going clockwise. From top clockwise along, the pressure increases. So we see P1 on our dial is greater than P2, and again, P1 is greater because the speed is less at V1. P2 decreased, P2 is less, the pressure has decreased because the kinetic energy has increased. This is only true when there's no change in gravitational energy. So again, pressure differences related to kinetic energy density differences. It's not a general rule because there are no other forms of energy that are involved. In a sense, the pressure is simply here to balance the energy equation. More complicated situation, from point 1 to point 2. Point 1, tube 1 is higher than point 2. So a number of energy systems can change. The kinetic energy density, the kinetic energy per volume, going from 1 to 2, going from fast to wider, slow. So the kinetic energy is decreasing, going from fast 1 to tube 2, slow. The gravitational energy density is decreasing because it's going from high to low. So both the kinetic energy and the gravitational energy are decreasing, going from fast to slow and high to low. So both of these guys are decreasing their energy. So another form of energy, another tank of energy in a sense, has to increase. Oops. But the total energy has to be changed. If total energy is not, the total energy has been changed if the kinetic energy and the potential energy are both decreasing. But total energy should be constant. So we're missing something. So energy, an energy conservation equation, is like accounting. We're accounting for all the forms of energy. We're not being good accountants if we can't keep the books straight. The bookkeeping is incomplete if we can't talk about the losses of energy without saying where they get lost to. So we need another energy form. We count for the leftover energy form, the leftover energy difference of both the potential and kinetic energy decreasing by naming a new energy system. This is the pressure. The pressure is simply as a catch-all. It's an energy density to balance the books, to be the good accountant. It's catching any mistakes in a sense. Kinetic energy has been lost, potential energy has been lost, so we have the pressure there to catch the loss. The pressure increases because both the kinetic energy and potential energy have decreased. So the pressure at 2 is higher than 1. So hence kinetic energy density and the change in gravitational energy density plus the change in pressure all balance out or all cancel. The decreases in kinetic energy and potential energy cause an increase in the pressure. Pressure of 2 is greater than 1. Here's in the equation, the same thing. Note, you should try to reverse from the previous illustration 1 and 2. Go from a wide tube to a narrow tube below and see what the result is. Can we explain these phenomena? Here we have a garden hose where water is coming out. Now we have a garden hose with a nozzle that's narrow, where water is coming out in a narrow opening. And we see the water, the path of water, is shooting out more straight. It's not completely straight, it's still falling thanks to gravity constantly acting. But its path is not as curved down as much without the nozzle. So what's happening in part A is the water is shooting out faster. It's taking a longer path to fall rather than almost falling straight down as in the water without the hose without the nozzle. So why is the water shooting out faster with the nozzle? Well, through a narrow opening, the cross-sectional area is small, so the velocity has to be great. The same current is coming out of the tube in both cases, whether there's a nozzle there or not. As long as the nozzle is open, the same current is coming out, coming from whatever where the hose is connected to. The same current is passing through that hose. But if it passes through a narrow opening, a smaller cross-sectional area must come out with a greater velocity. The same thing is happening in the water faucet. The water is coming out at some current through the faucet, through the opening, and then we see the water is narrowing as it falls. Why does the water narrow as it falls? Well, it's falling faster because it's falling. It's gaining speed, gaining kinetic energy as it's losing gravitational energy. So it gains the kinetic energy, it gains the speed. When fluid gains speed, not only is it going through a smaller opening to gain speed, but if it's the fluid column of itself gaining speed, then the column shrinks in cross-sectional area. It can also start rotating and twisting in some cases. That would be an example of the kinetic energy, the rotational kinetic energy, also coming involved. Another example that you can test out is tearing off a piece of paper. If you tear off a strip of paper, rather than the large paper that the picture has here, tear off a strip of paper and blow across the top of the paper, you'll see the paper gets lifted up. Well, why is this? Well, the air is flowing up top of the paper faster than it is below, as long as you're blowing only up along the top. So if the air is flowing faster up top, the kinetic energy of the air, the fluid, the top of the paper is greater speed, greater kinetic energy as it's being blown across. So if it's greater kinetic energy, some other form of energy must have dropped. In that case, greater kinetic energy density corresponds to lower pressure. So the greater kinetic energy up top of the paper, which means the pressure is lower up top of the paper, so the paper gets lifted up from the higher pressure below. This is the concept behind the lift of an airplane wing. An airplane wing is curved, so that you're seeing the illustration here, the curved airplane wing. When the air is flowing above the airplane wing, the air flows faster atop the wing. There's more distance for it to travel. And also the air ends up circulating around a little bit more, creating more of a distance for it to travel, more motion. If the air doesn't travel across the greater distance atop the airplane wing in the same time, there'd be little gaps of air not connected, which would be creating more situations of low pressure. So where the air is flowing faster across the longer distance up top the airplane wing, if it's flowing faster, it's increasing its kinetic energy going from bottom to top, which means it's decreasing its pressure going from bottom to top. There's greater pressure at the bottom, less pressure where it's flowing faster at the top, so that greater pressure at the bottom is lifting up or creating a lift up like a buoyancy force on the airplane wing. Same thing is true with this house. If the wind is blowing very fast across the A-frame roof of the house, then there's low pressure up top the roof where the fluid is flowing faster. Inside the house, the air is hardly flowing at all, so it's higher pressure relative to outside where the air is flowing faster, which can cause the roof to get lifted off, say in a hurricane. This is the same reason why umbrellas can sometimes fold upwards in rainstorms. The umbrella is similar to the A-shaped frame of the roof, where the air is flowing faster across the top of the umbrella in comparison to the air not flowing nearly as fast underneath, inside the umbrella. Baseballs curve for the same principle. Looking at the baseball, if the baseball is spun as it's moving, then where the baseball is spinning in the same direction as the air flowing versus spinning against the direction, there's a difference in velocity on one side of the baseball where it's spinning with the air versus spinning in the opposite direction of the air. That relative difference in velocity between spinning with versus spinning against creates a difference in airflow on either side of the ball. Where the air flows faster, where it's spinning against the motion, you have a difference in pressure, which is causing not a lift, but a pressure horizontal. Well, it could cause a lift and a pressure difference depending on which way the ball is spinning, which makes the ball take a curved path. Another way to measure fluid flow is known as a Venturi tube. You're looking here as a picture of a Venturi tube. Here we see fluid flowing through a wide part of a tube and then a narrow part. Again, where it flows through the narrow part, the narrow cross section, the kinetic energy is increased. It's flowing faster, so the pressure is less. So P1 has more pressure where it's flowing slower. P2 at the same height has less pressure where it's flowing faster. The tubes of liquid, of stagnant, of still water, are being pressed up by the pressure at 1 and 2. But the pressure at 2 is less, so there's less fluid to be pressed up with lower pressure at 2. So the heights of the tubes record the pressures. The heights of the tubes are acting as gauge pressures, gauging the difference in pressure between P2 and atmosphere. And the vertical tube is gauging the difference in pressure between P1 and atmospheric pressure. Thermal energy density, a biological example, would be blood flow. It doesn't have to be just liquids and gases, liquids of water. It could be blood. So here, these are arteries. These are actual pictures of photographs I purchased at great expense. This is a picture of your artery. You're seeing there's the plaques on your artery. Well, if you have more plaque, you have more resistance to the flow of your blood. Well, what does resistance do? resistance, like the warming of your hands, the resistance from your skin warms up your hands. Resistance warms up a fluid. So the more plaque you have in the arteries, the warmer your arteries get. They increase their thermal energy. If your arteries have a long length of plaque, more length of plaque means more resistance. So resistance depends on the amount of resistors, the plaque, and the length of the resistor. Note it's harder for the blood to flow through the narrow tube up top than the wider tube. So if your artery is narrow versus wide, there's more resistance in the narrow part than the wider part. The bottom tube, the wide tube, the blood can flow, more blood can flow without being obstructed by the plaque. Whereas the narrow tube, the blood is going to have to interact with the plaque. So the wider the area, the less resistance. The narrower the tube, the cross-sectional area, the more resistance. So we see the resistance to the rate of fluid flow, resistance to current, depends on length of resisting material, the amount, and the type of fluid. If your heart had to pump syrup versus water versus blood, your heart has to pump differently depending on what it's pumping. And it depends inversely on the area. Narrow is harder to pump the blood through than wide. So the mathematical relationship is resistance times a constant times the fluid property, syrup, water, thick fluids, dense fluids, the length of the tube divided by the area of the tube squared. So the area of the tube is very important. That's 8 pi, that's your constant. That's not an n, that's an eta, the Greek letter eta, which is the fluid property, times L, the length, divided by the square of the cross-sectional area, is the formula for the resistance of a fluid through a tube. The more resistance, the more thermal energy that gets created. So resistance makes arteries hotter and water pipes warmer. So a corroded copper pipe will be warmer than a smooth plastic PVC pipe with the same water flowing through. Now your heart has to compensate for pumping through different tubes of different resistances, and your heart pumps to begin with just to get the pressure differences to make the blood flow. Because remember, fluids flow by pressure differences. So you're looking here from your textbook as an illustration of the pressure differences from your heart pumping to make the fluid flow. When the heart contracts, we have a pressure peak called systolic pressure, and then the heart relaxes again called diastolic pressure. It's this pressure difference that causes the blood to flow through the heart and therefore to flow throughout the body. The heart pumps a current of blood. The plaque in the arteries resists the rate of blood flow. This is an artificial heart that can only pump a set amount, then the flow of blood is reduced. Meaning as the resistance increases, if the heart can't compensate, if it can't pump any harder, an artificial heart, then if the pump is set at one pressure and the resistance increases, the flow of blood, the current decreases. So the pump is creating the pressure difference. So the pump is equal to, the pressure difference was equal to the current times resistance. Current is I, resistance is R. So as the R, the resistance increases, the current decreases. This is of course not good. This would be fatal. But organic hearts are variable. The heart can pump harder. It can expand and contract more. So organic hearts are variable pumps. Thus the difference in pressure can increase to compensate for the distance resistance to keep the I, the current, constant. You need to have a steady flow of blood, a set current to give you nutrition to your brain and your other parts. So if you have more resistance, your heart has to pump harder, yielding little to no change in the current, as long as the heart can pump at the greater rate. But of course, the resistance keeps on increasing by getting more and more plaques from eating more and more donuts. Your heart is working or pumping harder, and eventually your heart can fail. So if plaque builds up in an artery so that its diameter decreases by half, how much harder does the heart have to pump to maintain the same flow of blood through the artery? Remember, the resistance depends on the cross-section, the square of the cross-section. So if you decrease an object by half its diameter, how much does the area decrease if the diameter decreases by half? And since the resistance depends on the square of the area, how much does the resistance increase? and therefore how much harder does the blood have to flow. From your textbook, there's another equation that relates resistance to current. This is actually the same equation, just rearranged different form. I, or Q, your flow rate or your current, again relates to cross-sectional area times the velocity of the fluid through the cross-sectional area. Related to a bunch of variables, the same variables as we just talked about, where that delta P is the pressure difference, the pump. So if you rearrange this equation, solve for delta P, the pump, then you'll see that you get exactly the same relationship we just had before, where the R is the cross-sectional radius to the fourth power. Just recall the resistance depends on the square of the radius. The resistance depends on the square of the cross-section, or the fourth power of the radius. Now there's complications to fluid flow that we haven't discussed yet. We've so far been dealing with the fluid flowing in streamlines that all flow exactly the same, where the streamlines at the edge of the tube flow the same way as at the center. But of course the edge of the tubes always have some resistance. It is some material, whether it's a lot or a little, there is some resistance. Whereas the fluid in the middle is just, in a sense, passing or rubbing the fluid on either side of it, not rubbing the sides of the container. So fluid flows differently in different locations along the cross-sectional flow. The streamline of the fluid flows fastest down the center and slowest at the edges. This is known as viscous flow.